Welcome back. So, we were discussing about the noise and noise power and how it can be calculated. So, let us go back to our last page, where we have said that the noise voltage square is V n square. It can be expressed as by Planck's blackbody radiation for h f b r by e to the power h f by k t minus 1, where h is Planck's constant, k is Boltzmann's constant, bandwidth b, f is center frequency, t is temperature, and r is the resistance. Now, in the denominator we have e to the power h f by k t, which in Taylor series can be expanded, and by putting some value of frequency which is quite higher than microwave frequency, and a nominal value of temperature 100 K and f is equal to 100 gigahertz, we can put into this constants, and we can find out h f is much smaller than k t. So, therefore, higher order terms in the Taylor series h f by k t square, h f by k t cube, etc., can be neglected, and we can take e to the power h f by k t minus 1, which is the denominator, is itself is equal to h f by k t. So, therefore, that V n square now stands as 4 h f b r by h f by k t, that is 4 k t b r. Now, you look at it very carefully, that is, now V n square does not have any term of frequency. So, it is frequency independent. That means, if it is a noise voltage, so it is a white noise, but obviously there is an assumption. The assumption is it is true for h f smaller than k t, otherwise we have to go back to the Planck's original formula. Now, let us see. Let us see, there is that resistance which is there, which is R, which is at temperature T degree, whose equivalent could be drawn as a noise voltage source V n, and is lossless or noiseless, I should not say lossless, noiseless resistor, which is the voltage is filtered by a ideal band pass filter of a bandwidth b hertz. This is ideal filter. Then the output is the noise power in out. That noise power can be transferred maximally if the load resistance is same as R. So, now we can write the noise power N 0 as the current, which is V n by 2 R current square into R. So, that is the noise power, and if we put the V n value here, it is 4 k t b r divided by 4 r square into R. That gives us k t b. This always we remember that noise power is equal to k t b. Noise power is equal to k t b. How it is derived, we so see. But if you look at it more carefully, you just reduce the bandwidth b, and then obviously the noise power will be reduced. If the b is reduced, the noise power is reduced. That means, for low bandwidth noise is less. We talked about the residual noise power has to be reduced. So, low bandwidth noise is less. Similarly, look at T. If I reduce T, then also noise power is less. So, as the temperature of the system subsystem is lower, the noise is less. If you recollect that our space segment discussion, we said that the hotspot or heat generated by the components has to be dissipated. So, so that dissipation was taken by a heat pipe, or it is exposed to the cooler temperature, and the temperature of the circuit or that particular component it reduced, it will generate less noise. But then from this also you can say, if B is made large, that is when B is made infinity, B is made infinity, the noise power will be infinity? No, this is not true, because B infinity means F is infinity, and in our basic thing we said that F HF is much less than kT. As we go on increasing F, this is not valid, this assumption is not valid. So, we have to, in those cases we have to go back to that original Planck formula. So, now from this we understand that noise power is equal to kTb, and that is in a resistance with a particular temperature T. Now, let us see, we have said that this is a resistance, but any of the devices that can have similar characteristics. Let us say there is a arbitrary noise source, which generates the noise power N0, and with the maximum power we can transfer it when the loads are matched. So, this can be equivalently said that as if there is a resistance at a temperature which is effective temperature of the resistance, not physical temperature, effective temperature of the resistance, which generate these noise power, and maximum can be transferred when the loads are equal, source and load resistance are equal. So, this is the effective temperature of the resistance. So, that means N0 now can be said as k TEB. So, any device which generates certain noise, thermal noise or any noise, can be put effectively as if it is a resistive source with a effective temperature. It is not a physical temperature, remember T E has said. That is that T E is equal to N0 by k into B. So, most of the components are characterized by this temperature, which is effective noise temperature. It is called effective noise temperature, that is T E, which is N0 by k B. Okay. Now, let us look at one of the type of circuits which often we come across, that is amplifier. With gain is equal to G. So, that can be modeled as there is a amplifier which has a gain G, and it has a effective noise temperature, because it is generating its noise by itself inside. So, it is the effective temperature T E. Now, this can be modeled as if this particular unit is having input power noise in I, which is equal to 0, which is generated by a resistance at t is equal to 0. So, we can call it a t 0, t equal to 0, or let us say t equal to 0, whichever way. So, input is 0 and it is giving output as a N 0, which is the noise it is generating to a load resistance R. So, this can be drawn as a equivalent as a noiseless amplifier with a gain G. This is a noiseless amplifier, and as if it has a input resistance R with the effective temperature T e, which is generating this N I. And since this is noiseless, G times that input will come. So, output will N 0 will come out of this, which is connected to the load. So, we can write N I is equal to K T E B, K T E B, that is N I, and N O is G times N I, which is K T E B into G, or that effective noise temperature of this amplifier is N 0 by K B into G. So, the amplifier which is having a physical temperature generates its own noise, and the effective noise temperature is estimated as N 0, the noise power which is generated, divided by K into the bandwidth and into the gain of that. Now, how do we measure? How do we measure this T e? There is a simple method which has two inputs at different temperature and measure the power. That is, let us draw it. Let us see, this is a device which is at temperature T 1, and this is another device which is temperature at T 2. These devices are different noise, different temperature sources or noise sources, and then we put the device under test, which has a gain, which has a effective noise temperature, which has a bandwidth, and then there is a input noise power coming. This device under test, based on its gain, effective noise temperature and bandwidth, generates some noise. So, the total noise is measured in a power amplifier, power meter. So, when the switch is towards the T 1 source, the measured output power is N 1. When the switch is towards T 2 source, the measured output is at N 2. So, we can write N 1 is the input noise, that is input noise multiplied by the gain of this, that is G K T 1 B, and the noise generated by itself, that is G K T E B. The input is having a temperature T 1 and the device has its own effective noise temperature T e. So, input is multiplied by the gain and the device itself generates GKTEB. Similarly, N2 will be GKT2B and its own GKTEB. Now, if you take the ratio of these two and we call a factor called y is equal to N1 by N2. If you take the ratio of these two, many of the things like a gain k, b will get cancelled and you will be left with T1 plus Te by T2 plus Te. From this we can find out what is Te in terms of y. So, by changing the side, that is let us say y is equal to T1 plus Te by T2 plus Te. So, we can say Te into y minus 1 is equal to T1 minus y into T2. So, Te is equal to T1 minus y into T2 by y minus 1. Since this effective noise temperature is supposed to be larger than 1, we have to make T1 larger than T2 and also T1 and T2 should not be close. In that case, the y will be very near to 1 and the denominator will be very small. So, the accuracy of Te will be lost. So, therefore, the T1 and T2, these two are kept far apart. Now, this effective noise temperature is we have measured. This is one way of characterization is of a component. There are other ways of characterization. So, normally components or subsystem are characterized by Te or the noise temperature. It is also alternately components are characterized by another parameter which is called noise figure. Now, the noise figure is a measure of SNR degradation from input to output. By definition, that noise figure is the ratio of input signal to noise ratio to the output signal to noise ratio. So, if it is a noiseless device or component, the SNR of output is same as SNR of input. That means, if the input has if the device is having some gain, the signal is elevated by the same gain and noise is also elevated by the same gain, and it is a noiseless device, it does not introduce anything. So, signal to noise ratio at the input is same as signal to noise ratio as the output. But for real device, that N0 is more than Ni into if there is a gain. So, signal to noise ratio is less at the output. So, that is the noise figure, if we denote it by F, is signal to noise ratio at the input and signal to noise ratio at the output is greater than, or in case of noiseless it is equal to 1. This is what is the noise figure definition. Now, let us try to calculate this noise figure in terms of noise temperature. So, there is a noisy device or network which is having a gain G, bandwidth B, and effective noise temperature T E. Let us assume the input to this is a source which is at normal temperature T0, 290 degree, and it is matched to this source. So, the power input to this noise device is the signal power and the noise power is coming as input. The noise power is generated because of this T0, but remember it is matched to this. So, the assumption is input noise power is matched to a resistor, assume resistor at, which can be taken as a 290 degree Kelvin for the timing temperature, that is normal temperature. And then the noise power output to the load is output signal power and noise power, that is total power output, is there is a gain G. So, G times the input signal power plus K G B times that input temperature plus effective noise temperature of this device or the noisy network. That means, the N0 is equal to G into K T0 B plus G into K T E B. So, noise figure F is S I by N I divided by S0 by N0. So, it can be said N0 by S0 here, or O means output, I should not say 0, it is NO by SO. So, Si by Ni is KT0B and N0 is GKB T0 plus TE divided by G into Si, that is SO. So, all these things get cancelled and resultant is 1 plus effective noise temperature by the T0, or the effective noise temperature of the device can be put in terms of F minus 1 into T0. Remember, for all these calculations, this term F is a ratio, not in dB, not in dB. we should write differently, because this nomenclature can confuse. So we should write T e is equal to f minus 1 into T 0. So if network or device is noiseless, then T e is equal to 0 and f is equal to 1. This note I am repeating, that is, noise figure is defined for matched input source, that is number 1 point, and second is the noise source which is at the input consists of resistor, an equivalent resistor at temperature T 0 is equal to 290 K. Some people may take it as 390 K normal temperature. It's as if it is equivalent to a matched source with a resistance with a temperature of 290. If there is a different temperature coming in, noise temperature coming in, then it is to be calculated with that. We have to remember this. So we continue our discussion for the next class. Thank you very much.